So the way I think about it is kind of in circles like this. I think that we have there is what we call mundane physics, and mundane here is not meant in a pejorative sense. It's the fact that if I throw this up, I can calculate how fast it goes, and how much time it'll take to come down, and so on. And that's classical physics that we developed more than 300 years ago. And that's actually very successful. Even today, when we send spaceships up and so on, we use classical mundane physics. So it's the physics of everyday life around us. And then, as about 100 years ago, we started realizing that when there were high relative speeds, then what would happen is that our notions of space time had to change, right? So, new notions of so we had to have new notions of space time, and that was the theory of special relativity. So, this was special relativity, and then we found that this itself, yeah. Can I use the black marks? Brackets? Yeah. Please also tell me if my writing is unclear. And this, of course, was subsumed in some bigger setting, which is the theory of general relativity, right? Which I guess all of you studied, also some have been exposed to some extent in the preparatory school. Is that fair enough? Or if you've seen some more, right? And so this is, of course, it subsumes, it gives you a broader framework on how to think about space time, and this is important when gravity is important, right? And then, we also learned in an orthogonal direction that when you looked at objects that were very small, that we came to quantum mechanics, and quantum mechanics had to do with, roughly speaking, a new notion of reality. It told us that, reality was not described in terms of what we classically thought it was described in, or what mundane physics says, and that, you shouldn't think in terms of a classical phase space, but rather you should think in terms of, space of wave functions, which is a different notion of reality, right? And this is what, maybe one of the most important things that comes out of quantum mechanics, which is that our usual notions of what we think of as a description of the world, our mundane notions, are not quite accurate. And in fact, the world is described by a different set of variables. And, we might think that a particle is here or it is there, but even that basic logic is simply not correct. And you can have a wave function where the particle is in a superposition of being here and there. And then, we started putting together these notions. And the framework that combines special relativity and quantum mechanics is called quantum field theory. And I believe that, many of you have also exposed to the framework of quantum field theory in the preparatory school. Even though it's not usually part of undergraduate curricula, I guess many of you have seen some quantum field theory before. Is that fair? Okay, great. However, we could now ask what happens if you try to combine quantum mechanics with general relativity, and that would be presumably some framework that subsumes quantum field theory. And this would be a theory of quantum gravity. And in fact, we have not constructed a successful theory of quantum gravity, a completely successful theory of quantum gravity so far. So, string theory is one effort to construct a successful theory of quantum gravity. And we've learned many new and interesting things about quantum gravity. But it would be fair to say that we don't have a theory of quantum gravity that describes the world around us and all the features that we see around us. And that's completely theoretically consistent as well. So, this is, of course, an important problem. It's an important problem because, in our world, we believe quantum mechanics is correct and we believe that general relativity holds. And so, it makes sense just from the point of view of theoretical consistency that we should have also a theory of quantum gravity. It's also important for questions about what happened at the beginning of the universe, which is a question that we would like to understand. It's also important because this theory of quantum gravity also forces us to ask ourselves questions and re-examine both gravity, general relativity, and also notions of quantum mechanics. So this is the broad theme within which all these lectures are going to be based. And so one could ask, why do we study the information paradox? Right. So these lectures, this module that I'm going to speak about, I'm going to give 5 lectures about, is the information paradox. And you might ask, why is it an important problem at all? And the reason the information paradox, so, the question is, why study the information paradox, right? Or why study black hole information? In fact, something that you will realize uh, and might already know about is that the information paradox is not really an important paradox for astrophysical black holes. If you ask about astrophysical, so the information paradox is about what happens when black holes evaporate, and I'll explain it in more detail either by the end of this lecture or next lecture. But roughly speaking, as I'm sure all of you know, it's some paradox about what happens when black holes evaporate and whether black hole evaporation is consistent with quantum mechanics. But in fact, this paradox is not important for the realistic black holes that we have seen around us. We have now observed in many different ways the presence of black holes in the universe. We know that black holes exist, but these black holes don't really evaporate because the temperature of the evaporation at which they're emitting radiation is much lower than the temperature of the cosmic microwave background, and so in fact they're absorbing radiation. And even if you were to leave a solar mass black hole, just in splendid isolation with nothing around it, it would take many, many, many years to evaporate. If I remember the figures correctly, something like 10 to the 67 years to evaporate, which is much, much more than the age of the universe, right? Which is about 13 billion years. So, the information paradox is not an empirical question about realistic black holes. However, the reason it's an important problem in quantum gravity, and this is the first point I want to mention, is that it forces us to think carefully about quantum gravity. And the reason is it brings about, it brings to the fore a tension between some principles of gravitational physics and some principles of quantum mechanics that we think should hold. And by thinking about that tension, we are able to make some progress on problems of quantum gravity. And in the end, it tells us something that is fundamental about quantum gravity itself. And so the reason we study the information paradox is because it teaches us about quantum gravity. And I'll try and explain how, you know, it teaches us some features of quantum gravity that might be much more accessible than questions of what happens when black holes evaporate. Okay? So I'll try and explain how it teaches us that quantum gravity in a setting, not in a setting that's experimentally accessible today, but in a setting that might be experimentally accessible much sooner than we start asking questions about black holes evaporating. Thinking about the information paradox reveals these features of quantum gravity, which we could have thought about even without thinking about the information paradox, but which we thought about because we thought about the information paradox. Okay? So, the reason we want to study the information paradox or study questions about black hole information is because it teaches us fundamental things about quantum gravity. And that's one way we have to make progress. Right? The reason we haven't made so much progress on quantum gravity is because it's not an empirically or experimentally accessible field, because the kinds of measurements that one would need to make are just so hard to make. They're beyond our current experimental abilities. Therefore, theoretical thought experiments of the kind, which put tensions between general relativity and quantum mechanics, like the black hole information paradox, are important because they force us and reveal principles of quantum gravity. Okay? So that's the reason this is an important problem. That's the reason it's attracted so much attention. Okay, so this is just something which I would like all of you to keep in mind about why it is that we are spending so much time on this. And the reason is that we learn something about quantum gravity, and hopefully by the end of these lectures, I'll have said something about quantum gravity that, as I said, you could have learned without thinking about black hole information, but that we learned because we thought carefully about black hole information. Yeah? Okay, good. So that's broad overview. Are there any questions about this broad overview? Did what I say make any sense? Yeah. Okay, I haven't said anything about the paradox itself, but go on.
If you visit quantum mixes, we have laser make then on digitally processes the get transformer modern it is hemisphere. So why boom get the information?
Oh, so okay, so first of all, we don't have non-unitary processes within the ordinary framework of quantum mechanics. If you think about measurement, the way one thinks about measurement, is that at all points of time, the Schrodinger equation holds, and what really happens is that the system gets entangled with an apparatus, and then there's some process of decoherence. Okay? So that's the way we think of measurement. We don't think of measurement as involving some some non-unitary process. So it's a very important principle of quantum mechanics that time evolution of the whole system is unitary. It's like and that's also an important principle of classical mechanics. You could have said that I roll this and this evolution looks like it's non-unitary because well, it's not stopping, but it it could have stopped, right? So it stopped here, and you could have asked, you can't really calculate what was the speed with which I put the chalk on the table or put this marker on the table. And you could have said, therefore, it looks like this time evolution is also dissipative, and all around us we see dissipative evolution. However, it's a very important principle of classical physics and also of quantum physics that time evolution is always unitary. If we give up the fact that time evolution is unitary, we'll run into all sorts of trouble. We'll have to reevaluate our entire theory. So we'll have to reevaluate all our principles of classical mechanics and all our principles of quantum mechanics. And surely a theory where time evolution is not unitary would not be quantum mechanics as we know it. It would be some modification of quantum mechanics. In quantum mechanics, time evolution happens according to the Schrodinger equation. And provided you take into account everything, including the apparatus, you, the observer, and so on, we believe the Schrodinger equation always applies. And therefore, time evolution is always unitary. However, this is a question. Yeah. No, no, no. It's not a question of time reversal symmetry. It's a question of unitary evolution. Okay, so that's different from the question of, is there time reversal symmetry in the system? And in the weak force and all other forces that we know, time evolution is always a unitary operator, okay, which is different from the question of reversibility. However, this is a question about the paradox. Maybe I'll postpone further questions about this itself to after we have introduced the paradox. Right now, the only point I wanted to make was the reason we are having these lectures at all is because they will teach us something about quantum gravity. Okay. Okay. Are there any other comments about this or questions or comments? Okay, good. So here is a rough plan that I had. I don't know if I'm going to follow this plan, but I'll try. So this is my plan. This is my plan for the first lecture. I'm going to talk next lecture about pure and mixed states. You don't have to copy this down. This is just so you get a sense of what's happening. I'm going to talk about, as I said, it teaches us about quantum gravity, and I think one of the things it really teaches us is about this phenomena called holography, but not really a slightly weaker notion of holography, which I'll come to, which is called holography of information. And then, if I have time, I'm going to speak about refinements of the paradox, okay, which also teach us something about quantum gravity, but maybe even deeper issues about what are the kinds of observables you might have to have in quantum gravity. If I have time, I'll come to point 4 as well. Okay, so that's a rough review. A lot of what I say, in fact, is in a pedagogical review that I wrote a few years ago, which things haven't changed very significantly in a few years. This is the archive reference. Do all of you know how to get a paper from the archives? Yeah. You go to http www.archive.org and you put in this number. And if you put this number, you'll get the paper. This is also a physics reports, but you don't need to look at the journal version. Always look at the archive version. That's always more up to date. Yeah. Okay. So this is a reference. Much of what I say, will be there in some form or the other. Uh, and so that's after and this review also has references to the literature otherwise, so you can also look at the review and then follow it up further if you want to look at details. So the review itself might not have details of all calculations, but will point you to where you can find details of the calculations. Okay, good. So that's about the logistics and a rough overview. I'm now going to say something about black holes. Okay, so this is the first part of what I wanted to say, which you've probably already seen, but just to make sure that we are all on the same page, I'm going to make a few comments about black holes and the geometry of black holes. Have all of you seen Penrose diagrams? Okay, good. So, let me draw the Penrose diagram of a black hole. Okay. So, this is a black hole that's formed from collapse. Okay. And this is called the horizon. This region is called Scri plus, okay, which is where future rays end up. And this, all this course will be, we'll discuss physics, but the physics that we are going to discuss is about this region of space. Okay. And so this region of space is what we're going to talk about, which is some region near the horizon, but this region is much after the infalling matter has gone in. And for the first part, we'll later talk about, but much before the black hole has evaporated. Okay. And then we'll start talking about what happens when the black hole evaporates. But first, I want to talk about what happens. We'll always kind of be in this regime much after the infalling matter has fallen in. For today's lecture, for at least the first lecture, we'll be talking about a regime which is much before the black hole evaporates. Okay. Now, why can we talk about this setup where we can be, much before, much after the infalling matter has fallen in and much before the black hole evaporates? Okay. And the reason is, as I'm now about to explain, that there's a scale, there's a difference in scales between, when the effects of the infalling matter die off and when the effects of black hole evaporation kick in. Okay. So the effects of the infalling matter, if you look at this Penrose diagram, what it tells you is, so this is the infalling matter. And this infalling matter, of course, not doesn't exactly follow this curve, right? Could be perturbations, there could be various things happening in the infalling matter. However, as you go along and you probe this geometry at later and later times, you find that the effects of the infalling matter die off, and they die off exponentially according to something called the No-Hair theorem. And they die off over a time period that's roughly controlled by the horizon size of the black hole. So if you probe the geometry and you wait for some time, which is some multiple of the horizon size of the black hole, then you find that you don't have much trace of what formed the black hole in the first place. Okay? So the black hole becomes like a vanilla black hole, which doesn't seem to keep trace of what fell in. On the other hand, if you wait for a very long time, as I said at the beginning, then the effects of black hole evaporation start kicking in. But because these two are different time scales, we can ask about physics at an intermediate time scale. And that's the physics that I want to describe now. So let me write down a few more equations to try and make this precise. Uh, so if you look at this full metric, okay, the full metric that describes this full geometry, okay, we have various descriptions of this kind of metric. In fact, one description is by Oppenheimer and Schneider, which is maybe 1939. I don't have the dates here. I forget, maybe 1939 or something. Okay. However, there was in fact a description by a Bengali physicist named B. Dutt, okay, who described this full geometry, okay, of collapse, or described, made important contributions before the full solution was given by Oppenheimer and Schneider. And actually, we don't even know much about B. Dutt, except that there's a paper by B. Dutt that we can still find, which is a couple of years before Oppenheimer and Schneider, that discusses these kinds of solutions. Okay, so this full geometry is a pretty complicated geometry. There's a simpler solution called the Vaidya geometry by P.C. Vaidya, which was set up later, which is not this kind of geometry, but which involves a shell, a null shell falling in this way. And so, but the point is that we can work out models where this full geometry, this full Penrose diagram, and the details of this full Penrose diagram can be worked out. Okay, and these were worked out a long time back. However, as I said, what we are interested in is this region. And for this region, we don't actually need this full geometry, which has this infalling matter, but we can restrict ourselves to a much simpler geometry, which is described by a very simple metric. That will be the metric that we want to focus on. Okay. So if you're interested in that region at late times that I marked there, then in fact we don't need this full Oppenheimer-Schneider metric, but rather we can get away by thinking of the following metric. The dimensions as well, and also the lower dimensions. What was that? Sorry. Also the lower dimensions. And therefore, this is I'll keep this D floating around when I can. This is an R. I'm sorry, my R is so erratic. It can look like a V or a nu or an R. So it's part of the test is that you're paying attention. You can figure out when it's which. Yeah. Okay. Okay. Good. And this mu is related to the mass of the black hole with some formula that's actually not going to be important, but I'll just write it down for completeness. Okay. Okay. Now, all of these factors are completely unimportant for what we're going to say. All that's important is this mu is like a mass parameter. It's linearly proportional to the mass. Okay. So all you need to know here is that mu is proportional to the mass. Okay. So this mu is like some mass parameter which tells you what the mass of the black hole is. Okay. And this is the parameter that enters into this metric. Okay. This metric is a very important metric because when we look at, when we look at that region, you see this, this metric has an important symmetry that that full metric doesn't have. Okay. So this metric has a symmetry which is that, it's invariant under t goes to t plus delta t. Notice that none of the components of the metric here involve time. Okay. So there's an isometry in this metric, which is that you can shift time, and the late time geometry of the black hole has an emergent isometry, okay, which is time translational invariance. And that's going to be important. So this has, yeah, just 1 second. Yeah. And that is clear from the metric that I wrote down. So that's only in this region. This whole geometry does not have time translational invariance clearly, right? Because the black hole started at some point, the matter fell in, and there are all sorts of complicated dynamics that's happening here. But if you look at the late time geometry of the black hole, then it does have this time translational invariance, and it's described by that metric that I wrote there, which is a very simple metric, which is different from the full metric that you need to describe this collapse, which can also be worked out, but is not going to be important for our purposes. So that's the first point I want to make, which is that the late time geometry of the black hole is described by a very simple metric, which we can write down explicitly, and which has this symmetry. Okay. Okay. Yeah. Question. Yeah. Is that a Zuckerberg? Is that the Zuckerberg trick in some sense? No, no, no. There's no Stuckelberg trick here. Why Stuckelberg trick? It's just obvious, right? If you change t, this metric remains unchanged. No, there's no gauge issue here. We're not. This is just. It's much simpler. Just look at this metric. You see, none of the components depend on t. So there is a killing vector, and that killing vector is just d by dt. It's that's why I wrote it in this form. It's the fact that if you change time, you see that this metric just remains unchanged. Is this so? There's no Stuckelberg transformation here. Yeah. What's the difference between mu? It's 8 pi to blah blah blah. So what you need to remember is mu is proportional to m. So there's a number, but that number is not important. So for instance, in the case of d, in the case of d equal to 3, this diameter is 2. These numbers are 2. So mu is equal to twice m. Okay, and it's a different factor in higher dimensions and lower dimensions, but it's always this. And so the important relation is this one. Mu is proportional to m. My handwriting is so bad that they all look like the same, but this is m and this is mu. Yeah, yeah. You said this is yeah, that's right. So what happens if you have because all this infalling matter is there, right? So if you have a star or a supernova, right now the sun, let's say the sun was twice as big as it is. Maybe the sun would collapse into a black hole, but clearly it's not time translational invariance, right? There's a sun, it's kind of, there's fusion, there's various things happening, it's dying out slowly. Maybe there's a supernova. All that is not time translational invariance, highly time dependent geometry, right? And then it collapses into a black hole and there's radiation and, the earth dies and whatever happens, all that is not time translational invariant. But at late times, everything settles down and there's, everything just looks like nothing is changing with time. That's what the black hole is at late times. Time translational invariance means nothing is changing with time. When you have a dynamical star that's spewing out radiation and so on, things are changing with time all the time. Okay, that's so at early times, this geometry doesn't have all that dynamics that I told you, but it has a dust collapsing. So there's a cloud of dust, which is big. It looks small in the Penrose diagram, but actually it's big. and it, that's because of the way you rescale things, and it just collapses. That's not time translational invariance manifestly, right? But at late times it is. Yeah. So you have to interpret it as a reduced. It's just a number. It's just a mass parameter. It's not a two body problem where there's a reduced mass here. Yeah, there's nothing deep about mu. I could have kept writing this m, but I'd have to put these factors. So it's, yeah. It's just, I mean, the only reason to write mu is to choose this constant to be 1. So I could write 1 minus mu. And I would never remember these parameters if they were not in my notes. So you don't have to remember them either. Okay, any other questions? Okay, what's the point for all of you to remember? And even if this is hard, it's this, that at late times, there's an emergent time translational invariance, and the fact that the metric is simple and you don't need the details of the collapse. Yeah? Okay, good. Now I want to say another thing. The next thing I want to say is that this region, in fact, looks a lot like flat space. Okay? That's the point I want to come to. I'll write it down later. But to do that, I'm first going to make some coordinate transformations and so on that you should know about anyway. And the point we want to get to is a point about the classical geometry of the horizon, which is that the geometry of the horizon, in fact, is pretty featureless. It, in fact, looks a lot like the geometry of flat space or empty space. Is there a question? Is there a question? No. Okay. So I'm going to introduce something called tortoise coordinates, which are useful. Okay. So these tortoise coordinates are often denoted by dr star, and they're just defined this way. Okay. So we can ask what, how do these, so it's a different radial coordinate. It's some redefinition of the radial coordinate, right? So this r, how was this r defined? This r was defined by saying that, this geometry, apart from having a time translational isometry, also has, a sphere at every point. And the radius of the sphere or the area of the sphere is what you use to define this coordinate r, is how you use to measure r. But we are choosing to redefine the radial coordinate. This is just a different coordinate, which is called the tortoise coordinate. Okay. Now, what are the properties of this tortoise coordinate? So, for instance, you know that at the horizon, the usual radial coordinate takes on the value r is equal to RH. By the way, maybe I should have done this earlier. If some of you are confused about Penrose diagrams, you don't have to, sorry, I'm going to take a step back. There's a point I should have made earlier, which I didn't make. So the virtue of Penrose diagrams is that, since I'm referring to it so many times, is that in Penrose diagrams, light rays are always 45 degrees. Okay. But sometimes they're a little counterintuitive, especially if you're not used to thinking about them. So there's an alternative way you can think about this, which is actually how Oppenheimer and Schneider might have first drawn it. Which is that you have a cloud of dust and it collapses, and it really looks like this. It's a big cloud and it collapses, and it kind of collapses to a point singularity here. And this horizon, I'm going to use the blue marker just for the horizon, is something that emerges, okay, and then it kind of stays like this. Okay. And this is r equal to RH. Okay, so that's another way of drawing the Penrose diagram. The reason, not of drawing the Penrose diagram, of drawing this collapse, the reason we don't draw it this way is because this r equal to RH point, which actually looks like it's at r equal to RH, is in fact also the trajectory of a light ray. Okay, if you put a light ray right here, it'll just get stuck. And light rays just outside go off, and light rays just inside go in. Okay, so this kind of diagram, which might conform more to our intuitive notions of radius and time, is not useful because it makes the causal structure not manifest, whereas this kind of diagram makes the causal structure manifest. On the other hand, you can also think of this process in terms of this diagram, okay, which makes it clear that the horizon is at a fixed radius. And in fact, at late times, which is when we are talking about, the matter has all fallen in, and so there's nothing around. Okay, that's the next point I want to make. Okay, I hope this is clear, that you can think of this process also in this way. Yeah. What happens to light when you own that, right? Well, on that line is exactly a null line. So if you have light which is exactly on that line, it would kind of just stay stuck. It would keep moving up. If it was just outside, it would go out. If it's just inside, it would go in. Yeah.
I just want to reach you hope that you start with the Einstein equation and you pick a t tends to some large number limit, and after that you end up with that space.
Well, this metric is a metric that describes a black hole. It solves the Einstein equations in the vacuum. It solves the vacuum Einstein equations. Okay. Now you could ask, why are we solving the vacuum Einstein equations? It's because maybe it's clearer in this geometry. You see, because everywhere here is the vacuum. There's no matter left. So this geometry is solving the vacuum equations, except at r equal to 0 where there's a singularity. So there is a singularity in the geometry. But everywhere else, it solves the vacuum Einstein equations. Now,
Even the vacuum goes, I have the dust.
no, we do take into account the dust. So I said that metric solves the vacuum Einstein equations. You can consider the full metric, which Oppenheimer and Schneider or B. Dutt or whoever found. And they considered a metric which also had dust as a source. That metric doesn't solve the vacuum Einstein equations. It solves some different equations which has dust as a source. But if you take this metric and you go to late times and you look at this region of space, then this region of space is described by that metric which solves the vacuum Einstein equations. So you don't have to take into account the complications of the dust, which leads to a complicated source and a complicated metric, but rather you can deal with a simpler metric if you're interested in the physics in this region. Yeah, is that clear? Are there any other questions? Okay, good. So, and the next point I want to make is still about that region, just about the classical geometry. It's convenient to move to these coordinates, which are called tortoise coordinates. Okay. And what is so let me just say a few things about these coordinates. So the first thing is, as r tends to infinity, what happens to f of r? It becomes 1, right? Yeah. So f of r becomes 1. Therefore, as r tends to infinity, r star, tends to infinity, because dr star is just dr, right? As r tends to infinity. So you can start integrating from wherever at large r, at r equal to whatever large value you like. But as you go to infinity, dr star will also go off to infinity. Okay. So at r tends to infinity, f of r tends to 1, and therefore r star tends to infinity. Is this clear? Okay. The question is, what happens as r tends to rh? So there's another interesting point here, which I marked there, which is that there's a point here where f of r tends to go to 0. Okay. So f of r goes to 0 at r equal to rh. This is the definition of rh. This is the definition of where the horizon is. So this rh is just given by solving this equation. It's just rh to the power d minus 2 is equal to mu. So rh is equal to mu to the 1 by d minus 2. Okay. You see this? So at this point, f of r vanishes. Okay. And we are interested in asking what this tortoise coordinate does as r goes to r horizon. That's also this point, r equal to rh. And in this diagram, it's this line. Okay. It's the same line. Yeah.
RH is the radius.
Yes. RH is radius of the horizon. Here it's the root of f of r. Okay. This blue line is also the horizon. Yeah, it's the same line. This blue line is that blue line. Okay, it's r equal to rh. It's the point where f of r goes to 0. Okay, so f of r goes to 0 at r equal to rh, and we want to ask what r star does there. Okay, so so as r equal to rh, so more precisely, as r tends to rh, okay, f of r goes to twice k into r minus rh. So of course it goes to 0, but we can also ask at what rate it goes to 0. Okay, and this k, which is f prime rh by 2, is called the surface gravity. This is just a definition of what the surface gravity is. If you had lectures on black holes, you would have seen more about the definition of why surface gravity is called the surface gravity, but it doesn't matter. For us, we just want to know that f of r vanishes. What I said here is just that f of r has a root at mu is equal to, at rh is equal to mu to the 1 by d minus 2. And at that, as r tends to rh, f of r goes to 0. But of course, it goes to 0, can't just go to 0, it goes to 0, it drops off as R comes closer and closer to RH. And the constant of proportionality is called kappa, and it's just a derivative of S at RH. Okay, this is called the surface gravity. Okay, good. So what happens to this this R star? Well, you can check that if you look at this equation, we find that dr star is dr by twice cup k into r minus rh, and then you can solve this equation, and you will find that r star goes like 1 by twice k into twice k. Now this, notice I've put in some integration constant here, which in fact will be useful for what we do later. So I say that as r tends to rh, maybe I should say r. So this is the solution for r star when you're close to rh. Okay. Of course, there are higher order terms when you go away from rh. Maybe I shouldn't write equal to. I should write tends to. Okay. So as r tends to rh, dr star tends to this, and r star tends to this. Of course, r star tends to r as you go far away. Okay. So what I said was I'm defining a new coordinate, which is called the tortoise coordinate, which is defined this way. And as r tends to infinity, r star tends to r, it just goes off to infinity. And as r tends to rh, r star becomes a log of r minus rh. Okay. And the fact that there was a 1 by 2k was fixed by this 1 by 2k. The fact that there was a twice k here was not fixed, but I chose it with some prescience. Yeah. Okay. So for those of you who are getting lost in these coordinate transformations, if you have not seen it before, the point I'm heading towards is I want to say that the geometry of this region is a lot like flat space or a lot like empty space. Even though if you look at this metric, it looks like f of r is going to 0, so it looks nothing like flat space. It looks like this geometry might have a singularity. In fact, if you look at the Oppenheimer-Schneider paper, they will talk about this region as the black hole singularity. And even as late as if you look at the Feynman lectures on gravitation, people thought this region f of r going to 0 was some kind of singularity. And even today, if you speak to people who do numerical GR, they'll tell you that f of r, they'll call f of r equal to 0 the singularity. But in fact, this is not a singularity. What the point I'm heading towards through all these coordinate transformations is that f of r tends to 0 is just a region which looks like flat space. Okay, so if you're getting lost in this, just remember that's where we are heading. Okay, good. So the main point is that maybe I'll go here. Maybe I can go here. So the main point is that we can now go to make a change of coordinates. And the coordinate change we make is yeah. What? Well, I don't know what you mean by Cartesian coordinates. We were working with coordinates that in which the metric looked like this. So Cartesian coordinates is usually used in the case where the metric just looks like a flat metric. These are just, this is some choice of coordinates in which the metric looks like this. So you can ask now what is the interpretation of T and R and so on. The interpretation of R is that there is a sphere at every point in the geometry, and R squared is what determines the area of the sphere. The interpretation of T and R is in fact maybe clearer on that diagram. It is a notion of a time coordinate, okay, of T. It is a notion of a time coordinate, but what kind of time coordinate it is somewhat complicated. It's a time coordinate that kind of goes off to infinity here, as we'll see in a minute. Yeah. So, what did I do? Why did I skip a minus? This is my definition. Huh? maybe someone used the definition with a minus sign, but say I think I want to use this definition, which I think yeah, no, I think it's good for me to use this definition because it's consistent with this. You could use a different definition. You want a minus here? With a minus here? It does. In the U? You want a minus here? Okay, maybe you can define it that way, but I don't want to define it that way. It's you can in fact, I'm not even sure why that definition would be very good, as we'll see in a minute. Okay, maybe you can also change others. Maybe you can put a minus sign there and put a whole bunch of minus signs and make things work. Okay, but it doesn't matter. Yeah, if you put a t first, then it's the same thing. If you write a minus of t minus r star, that's same as r star minus t. Okay, so then there's no minus sign. Yeah. Okay, but so different conventions will work. I think this convention is consistent, and certainly if I try and change it now, I'll get confused. Okay, so we'll keep this convention. Okay, the point of this is that if you look at du, okay, it looks like minus into dr star minus dt. Yeah, what?
You said that r is 0, the space is that flat.
As r tends to 0. No, I never said anything about r tends to 0. Where did I say r tends to 0? F of r tends to 0. Somewhere I said f of r tends to 0. Here. Here, f of r tends to 0.
0.
Yes.
So then in that case, the space looks flat. Doesn't it think that the area should traverse slowly?
No. So first of all, f of r tends to 0 here looks like something very bad is happening. Because it looks like the coefficient of time is going to 0, and this coefficient here is going to infinity. So in this coordinate system, f of r tends to 0 looks like a singularity. That's why I said for many years people thought that f of r tending to 0 was a singularity. And even today, if you talk to people who do numerical relativity, they really refer to f of r tending to 0 as a singularity because that's where their numerical codes break down. However, f of r tends to 0, I now want to explain to you, is not a singularity. It's just a completely normal region of space, which is in fact flat space. So that's the point I'm now trying to make. Yeah. Okay. Again, dv is equal to dt plus dr star. Okay, so I just differentiated this, and this is what du is and what dv is. Okay. So in particular, if you look at minus du dv, it looks like minus du dv looks like dr star squared minus dt squared into e to the twice kappa r star. Okay. 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 However, if you look at this solution, okay, then you will see that e to the twice kappa r star is also equal to twice kappa into r minus rh, right? As plus other terms. So e to the twice kappa r star is also twice kappa into r minus rh. You see? And that's what you also get here. So this is in fact f of r, right? So you see that this whole metric can be written as f of r tends to 0, we get ds squared is equal to minus du dv, okay, plus r squared d omega squared. And now you see that in these coordinates u and v, the metric does not have any singularity as r tends to 0, as r tends to rh. Okay. In fact, as r tends to rh, this part is just some sphere, okay, and this part is just like two-dimensional flat space. It's just du times dv. We could have introduced, have you seen this metric as a metric of Minkowski space? This is the metric that you would get for Minkowski space if you just introduced null coordinates. Right? If you just wrote some coordinate system that looked like dx squared minus dt squared, by going to coordinates t minus x and t plus x, you would have written the coordinate system in this way. Okay? So you see that in these coordinates, the metric does not have any singularity as r tends to rh, even though in these coordinates it looks like the metric does have a singularity as r tends to rh. Okay? And the fact that it doesn't have a singularity in these coordinates tells you that it was just that this coordinate system was a bad coordinate system. And if you go to the right coordinates, then you find that the metric does not have any singularity. Okay. Okay. So that's the point I wanted to make here, which is that in these coordinates are, by the way, called Kruskal coordinates. Okay, but and so I'm sure you probably saw them previously in your lectures. And so however, the point of us introducing Kruskal coordinates, so I've made 2 points. Actually, maybe I can write these points here. Yeah. So I've made only 2 points so far. One of them is that at late times, as a t goes to t plus delta t isometry. Okay. And at late times, the horizon, or this is true at all times, horizon is just like empty space. Okay, it doesn't have a singularity. So, if some of you are having difficulty in following all these coordinate transformations and so on, then you should remember that these are the only 2 physical points we have made so far, which is first this one, at late times you get a t goes to t plus delta t isometry, and at late times the horizon, which is the r tends to rh. The reason I'm saying late times is we're always discussing late times. At some point I'll stop writing late times. Is that the horizon, which looked like it was singular in this, actually is not singular, and it's just like empty space, which you can see by making this coordinate transformation to these coordinates. Okay. Is this clear? So please keep these 2 physical points in mind. If you can get all of these coordinates, this is what I've written here is pretty standard. You'll find it in many textbooks in GR. But if you're getting confused with these coordinate transformations, at least remember these 2 physical points. Is this good? Okay. Good. So let me just say one more thing about coordinate systems, which will be, might be important for us in the last lecture if we get to it. But and it sometimes is a point of confusion. If you look at this metric, okay, what happens as you go to r smaller than rh? What if you go inside? And this is the region inside the black hole, which is this region. This region is r smaller than rh. And you can see it from the other diagram that I drew in erase, where the horizon was just at r equal to rh. And so you could go to r smaller than rh. What is the sign of f of r then? F of r is positive for r, for r large, but for f of r, for r smaller than rh, f of r becomes negative, because this becomes negative. Okay, so for r very small, yeah. So minus f of r becomes positive. Okay, so this dt squared, this t coordinate, now starts behaving like a spatial coordinate, and the r coordinate starts behaving like a time coordinate. Okay? So sometimes you will hear this phrase saying time and space interchange, whatever inside. But this is nothing. This is just a feature of the coordinate system you're using, and the reason r becomes a time coordinate is because once you're inside the black hole, nothing, no force, not even light, can prevent itself from moving to smaller and smaller values of r. That's the physical reason why once you're inside the black hole, r becomes like a time coordinate, because you're inexorably driven to smaller and smaller values of r till you end up at r equal to 0. Okay, so just as time passes, you have to go to smaller and smaller values of r. Okay, so in the black hole interior, you'll find that the roles of this coordinate and this coordinate change signs, but this is not something that's very deep. It's just a feature of the coordinate system. If you were to here use coordinates which correspond to t is equal to v plus u and x is equal to v minus u, then you would find this t is always behaving like a good time-like coordinate, and this x is always behaving like a good space-like coordinate. It doesn't change sign across the horizon. However, because we chose these funny these coordinates are convenient coordinates. Because we chose these coordinates, it so happens that the role of t and r interchanges, and once you're behind the horizon, it's r that starts behaving like a time coordinate. And the physical reason for that is that you are necessarily driven to smaller and smaller values of r. So with increasing time, r necessarily increases with increasing physical time for the observer. Okay, so that's what happens once you're inside the horizon. However, this will not be important for us. This is a side comment. It might become important for us if you go to the last part of the lecture where I'll speak about refinements of the paradox. For a lot of what we're going to talk about before that, yeah, just 1 second, please. Just 1 second, please. Yeah, for a lot of what we're going to talk about before that, we are not going to be talking about this feature or what happens inside the horizon. Yeah, so that's what I wanted to say. Yeah, go on. Yeah. We do this activity here, and it's also true inside the black hole until you go very deep inside. Remember the other diagram if you like. This is what the horizon looks like. So if I'm here or if I'm here, is T mu nu still 0. So until I go to r equal to 0 or very close to r equal to 0, I don't have to worry about it. I'm still in empty space. Okay? So what I said here was true here. I don't know if you can see the arrow. What I said right now about behind the horizon. And what I've been saying otherwise is about here. And this patch is some patch here at late times. And this is all empty space, both outside and behind the horizon. And so remember, the horizon is like empty space. So it can't be that just when you go behind the horizon, there's some matter or something. So it's important that just behind the horizon, just outside the horizon is basically featureless. It doesn't, there is nothing which changes. It's all empty space. I mean, something changes globally in that if you're in a spaceship, you might cross the horizon. This is something people say. We could be crossing a black hole horizon right now, and we wouldn't actually know it. What would have changed is that our future would have been sealed. Once you're behind the horizon, it is necessarily the case that you will hit the singularity in the future, whereas once you're outside the horizon, you could go out. But that's a global statement. Locally, nothing is different. So outside and inside doesn't matter. If you think of this, if you find this diagram confusing, think of this diagram. Yeah. Okay. Yeah.
I was wondering about yesterday. You said they are passing the horizon, the space, especially economic as temporal.
No, the t coordinate becomes a spatial coordinate and the r coordinate becomes a time coordinate. It's not the component. There's always one time coordinate in the metric and one space coordinate. It's just, this coordinate system is bad, and behind the horizon, t and r change signs. Yes.
Who are to the time first. Actually, we can travel back or backing guy.
No, nothing like this is happening. It's a choice of coordinate system. I want to emphasize. It's not that you can travel back in time or anything like that. It's just that we chose a coordinates. I'm giving names, right? So let's say somebody came and said, tomorrow I want to write the metric of Minkowski's space as minus dx squared plus dt squared plus r squared, or plus something plus dy squared plus dz squared. Is this metric the metric of Minkowski space or not? It is. Just because I chose to use x and t doesn't change anything, right? It doesn't mean I can travel back in time or anything like that. It's just that I was kind of dumb, so I chose to call time x and xt. But that's my fault. It doesn't. Nothing physical has happened, right? This is still the metric of Minkowski space. What symbols I use is not important. That's what's happening there.
It's changing.
Well, the coordinate system is becoming the coordinate system is becoming singular, because f of r goes to 0 here, and 1 by f of r goes to infinity. So some components of the metric go to infinity. Therefore, the coordinate system is becoming singular, and that's also what's leading to this fact that this t is a time coordinate outside and it's a space coordinate inside. It's because the coordinate system became singular because some components of the metric became infinity. But that the fact that some components of the metric became infinity doesn't mean that anything physically bad happened to the metric. And if you go to these coordinates, you can see that nothing physically bad happened to the metric. Rather, you went from u negative here, u being slightly negative here, to u being slightly positive here. So you just crossed, you see this u goes to 0 at the horizon. So this horizon is also u equal to 0. Okay. And so all that happened is you cross u equal to 0. But if you cross u equal to 0, big deal, nothing happens, right? That's the metrics clearly has no problem there.
Lopi to that while is it shower? Happy man, like this is here. Should I?
What should diverge? This R squared? R squared, you mean? You mean R mu nu squared? No, no, that doesn't diverge at the horizon. Why would anything diverge? As you go towards the singularity, it's different. But at the horizon, nothing diverges. If you're in a big enough black hole, that's almost zero. So all so any scalar, like if you look at R mu nu squared or R mu nu rho sigma squared, does not diverge. It's completely non-singular at the horizon. Yeah.
In this picture, are you not interpreting that from the coordinates that were in
What do you mean? What physical picture?
like what's happening like the time it's not reversing or it's not keeping.
Nothing is flipping. That's it. That's it.
So how are we using the coordinate system? Yeah.
No, no. So, the thing is that we had some coordinate system which we wrote down, which was confusing. You should always go to a coordinate system which is non-singular. Once you go to a coordinate system which is non-singular, you can read off the physics completely clearly. Remember, one thing about general relativity is that coordinate systems are just labels you attach. If I choose a wrong labeling, I could choose a labeling so that this line was x equal to infinity, for instance. Right? And beyond this line, x went from being plus infinity on this side to being minus infinity on this side. I can choose a coordinate system like that, right? It would be redefining my usual coordinate to be, 1 by x minus whatever this value is. I could do that, but that's my fault. That's my problem. And I could write down a metric in this coordinate system, which would look like a very ugly metric. It would look like it's going singular here. But that is just, it's my problem because I'm choosing bad coordinates. You will come and say, look, I can change coordinates so that it looks completely smooth. So all we have done here is we have changed coordinates so that the horizon looks completely smooth. And from that, it becomes clear the horizon is completely smooth because once it's smooth in one set of coordinates, then it must be smooth. That all, invariants, coordinate invariants that you can write down will be smooth. Okay? So the only point I wanted to make here is that these coordinates become bad at r equal to rh, but that's not a physical singularity. It's a coordinate artifact. And in fact, in these coordinates, you can see that this region is just a region where this u goes to 0. That's all. It's not special. Well, one way you can be sure if it's a physical singularity is by computing a coordinate invariant, like r mu nu rho sigma squared. Okay. If you compute that and you find it diverges, then it's a physical singularity because these scalars are invariant under coordinate changes. So if you can compute r squared or something which is an invariant, some invariant scalar made out of the curvature, then you would know that it's a real singularity. It's not a coordinate singularity. Okay. Alternately, if you can, but to say that it's not a singularity is easier because if you can go to a coordinate system where it's manifestly smooth, then it's not a singularity because everything you compute will be smooth in that coordinate system, right? To see it's a singularity, you have to compute some invariant and see it's a singularity. Here we didn't need to do that. We just went to a coordinate system where everything was smooth. That's enough. That's sufficient to show that I don't need to do any calculation. Now, you could do the calculation, but it's obvious nothing is going to diverge at r tends to rh. There's just nothing here which is going bad. So why would anything diverge? Yeah. Okay, yeah.
You're saying that I think is
This one? This one? Oh. This one? Yeah. The r square, the omega square is a separate two-dimensional space. So this is a metric which looks like a two-dimensional space times some other two-dimensional sphere. Okay. Just at the horizon. Of course, remember, this r is not a separate coordinate. This r is actually a function of u and v. Okay. If I, where did I write u and v? If I take this and I look at u into v, okay, that gives you 1 by k square into e to the twice kappa r star, which is related to r by this formula. So if I solve this r is actually a function of u and v. It's not independent of u and v. It's actually a function of u and v. But if I just look at this part, okay, then it looks like some two-dimensional space cross some s2. Yeah. Okay.
will we do something what
Yeah. Go on, yeah.
so like some sort of things all we notice any legal take sleeping or
What do you mean by do we notice any physical change? The whole point here was to say that when you're crossing the event horizon, locally nothing bad happens. Locally, the event horizon is just a point in space, like any other point in space.
We had a we could do the measurement in our TBS level. But now whenever we are in that trial, have to shift our body.
No. It's like this. It's like the example I gave you. What do you mean? Let me give you this. Let's go there. Uh, can you guys see here? Let me draw a line in space. Yeah, this is x equal to 1 in this coordinate system, right? And I'm going to choose a bad coordinate system, which is x Suvrat is equal to 1 by x minus 1. Okay, this is my coordinate system. But now this coordinate system is very bad. Look, it's going to infinity here. It goes to infinity here. This capital X, it goes to infinity, and here, on this side, it goes to minus infinity. But that's there's nothing bad happening. This is just my problem. I shouldn't have chosen that coordinate system. So geometry. Uh, so I now want to derive the form of Hawking radiation. But once again, I'm just going to give you a sketch of the derivation. Yeah. So what should I erase? How soon is this? Okay. So I now want to consider. Sorry, I don't want. I'm not supposed to use this. Huh? Okay. So consider some field that satisfies box minus m squared phi equal to 0. So now I'm going to change gears. So far, I've made some comments about the classical geometry of the black hole, okay, which all of you should know. Regardless of whether you learn about the information paradox and so on, this is something we learned about the black hole. And all of you should be clear about everything I said. Everything I said so far is just completely textbook material. It will be found in all textbooks on GR. And so you should just be familiar. Don't worry, I'll get it. I'll get it first. Thank you so much. Yeah. Thank you. Thank you. I should find a better place to keep it. I'll keep it here. Yeah. Okay. So everything I said so far is something that's pretty standard. You should all know it, regardless of this. Now I'm moving on to talking about quantum fields propagating in the space-time. What I'm saying now is also pretty standard, but it's not found in all textbooks. One place you would find descriptions of this is in textbooks on QFT and curved space-time, like the book by Wald or the book by Birrell and Davies. But some of this is still also sometimes in the research literature. Okay, so some of the points that I'm making now are not always emphasized in textbooks, even though what I'm saying is pretty standard, but it's not as textbook material as everything I said before. Okay. Okay, so the question is now, what do we have to do with I want to analyze this equation, and I want to analyze this equation in these original r these r star t coordinates that I had. Okay. So do you remember what box looks like? Will someone tell me the formula for box in terms of the metric? Okay. Yeah. Okay. So box has this formula. Okay. So you can work out, what happens if you look at that coordinate system, and in this d r star coordinate system, can someone tell me what root minus g is in this d, t, and r star coordinate system? Yeah, it is the square root of them. That's the definition. But can someone tell me what it would be in the? I haven't written it down. So in the r star t coordinates, not in the r t coordinates, in the r star t coordinates for the metric we were considering, what is square root of minus g? The answers. Okay, I'm going to give it to you as a 2-minute exercise. Okay, can all of you just try and work out in your notebooks in the metric in r star t coordinates? So we have r star and t, right? What is square root of minus g? Okay, you just have to work out what this is. I'll just give you guys 2 minutes. Yeah, don't shout out the answer, but just write it in your notebook, and then I'll yeah. So so we in the r star t coordinates. Okay, so we want to be in, square root of minus g is not a coordinate invariant. It's a determinant of a metric, but it transforms under coordinate transformations. So when I ask you this question, I have to tell you which coordinates I'm in. So I'm in the r star t coordinates. Okay, I'm just going to give you 1 minute, and then I'll tell you what the answer is. But it's 1 minute of a useful exercise. Okay, so just make sure you're familiar with the metric. Huh? What's that? No, I can't see who's saying, but don't yeah, don't say the answer. I'll just say the answer in some time. Just work it out for yourself. Yeah, it's not. Uh, yeah. Okay, okay. So we're through with 1 minute. So I'm going to just tell you the answer. You see, in these coordinate systems, remember the metric look like dt squared, into f minus dt squared into f plus dr star plus dr squared by f. Once I go to these coordinate systems, it looks like s into minus dt squared plus dr squared, right? So in these coordinate systems, the metric looks like ds squared is f of r into minus dt squared plus dr star squared plus r squared d omega squared. Yeah, this r is an implicitly a function of r star. We don't have to write out what it is explicitly, but this is the metric in the r star t coordinates. Okay. So what is root minus g? Well, it's just f of r first of all, because that came from here. There were two factors of f of r, right? So when you multiply it, you get f of r square. You take the square root. Okay. Here there are actually many factors. Okay, there are d factors here because remember we are in d plus 1 space time dimensions. Okay. Sorry, there are d minus 1 factors here because we are in d plus 1 space time dimensions. Okay. So from here you get a factor of r to the d minus 1, and then you also get a factor of the metric on the sphere. There's also some metric on the sphere, and you get that. Okay. So this is the answer for square root of minus g. Okay. Okay. Those of you who got it, that's good. But those of you who didn't, like, please make sure you get this. It's just a simple calculation by realizing that the metric is this. Yeah? Okay, good. What about, we also have the inverse metric. So G star star is equal to GTT, and both of these are equal to 1 by f of r. Okay. You see that? Okay. So, okay, we also see, sorry, by writing the metric in these r star t coordinates, what one of the advantages of working in this r star t coordinate system is. I just made a big deal previously about how these uv coordinates are very useful, and they are useful. But then you could say, why are you now solving the wave equation in these r star t coordinates? It's because the r star t coordinates are much easier to work with when you're solving the wave equation. That's in fact why we use them, because the t goes to t plus delta t isometry is obvious in the r star t coordinates. Okay? And you can see that in these calculations. If you wrote this, in that coordinate system, then you would have some trouble as you went away. This metric is very simple. If you are right at r equal to r star, as you go away, it starts becoming more and more complicated. Okay. So this metric is kind of nice, even though these coordinates are not great everywhere. This metric is nice to solve the wave equation. Okay? So if you write this wave equation, you will now find that this wave equation looks like 1 by f of r into r to the d minus 1, some d star into r to the d minus 1. And here the factor of square root minus g and the g star star will cancel. Okay, this f of r will cancel. Okay. Okay. So this is a wave equation which was box minus m squared now looks like this because I'm just implementing this formula. This has only diagonal terms. So look at the g star star term. Okay, and look at the the star star term gives you an f of r and then 1 by f of r from here. which cancels with this f of r from here. You're left with this factor of r to the d minus 1. D star means derivative with respect to r star. I hope that notation is clear. And we also have a derivative on phi. So I'm just implementing that formula for box. Okay, all of you with me here, I'm seeing some blank faces. So if you're not with me here and you're confused about how I converted that equation to this equation, like please ask me questions. Yeah. This is dt. Sorry. Sorry. No, kind of, I'm sure in Bangladesh also, in India, we used to have all these exams, these board exams and so on. And I would always have a really hard time because my handwriting was so bad. So, if the examiner doesn't understand, it's a big problem for you, right? If the person who's grading. As you become older, the thing is, it becomes the other people's problem to understand your handwriting. So, when you're younger, it's your problem. Yeah. What's B? There's no B. This is a box. This is a box. It's not a B. Sorry. This is box. And this box is the Laplacian on the sphere. Yeah. Okay. 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 Is it clear how we got this equation? Yeah. This equation just came from implementing this and just looking at where the factors of f of r were. Okay. Okay. Good. And realizing that some factors like g omega just cancel out. So there are some factors which you just cancel between the root g here and the root g here. Okay, so if it doesn't appear in the derivative, you can just cancel it. Okay. Okay. Good. So yeah. Del star means that. Yeah. Okay. Good. So however, now I want to point out now I want to point out a simplification in this equation that occurs as near the horizon. Okay. So near the horizon, what happens? Okay. So near the horizon, 1 second. Near the horizon, what happens? Okay. Near the horizon, f of r tends to 0, right? Okay. Now f of r tends to 0, so this term becomes very important. This term becomes very important, but these terms are not so important because they don't have a factor of 1 by f of r. You see? So near the horizon, only these two terms become important. Now, of these two terms also, what is dr star? Notice that d star r, okay, is equal to f of r. That was our definition of r, right? Of f of r star. So when this d star acts on this r, it gives you a factor of f of r which cancels off the 1 by f of r. You see that? So near the horizon, which is at r, as r tends to r edge, what happens is that this geometry, this equation just becomes d star squared phi minus dt squared phi is equal to 0. Okay, because those are the only two terms that remain. The mass term is not important because it also does not have an f of r. Okay, so near the horizon, we don't have to care about the mass term, the interactions, the angular term. And by the way, here I was writing on a free field equation. If I wrote down an interacting field equation, so that here I had some v of phi, then this v of phi would also not know about the f of r. Okay, so this v of phi, sorry, maybe I should. This is some source I need to be. I haven't written down what v of phi in the Lagrangian is. Just imagine it's some right hand side of what we put here. Then you see that this would appear here and would also not have an f of r here. Okay, therefore the interactions also don't matter in this limit. So when you're solving the wave equation near the horizon, the wave equation near the horizon simplifies to a very simple equation and it just becomes this, independent of the angular momentum and all sorts of other stuff. Okay, so this is another feature that you should know about solving quantum fields in the background of a black hole. Yeah. What about the well, so what boundary conditions are you worried about here? Well, here I'm just separating variables for now. For now, I haven't written down any solutions. In fact, near the horizon, usually you don't impose any boundary conditions. I'll say something about when we pick solutions. I'll say something about what kind of boundary conditions we pick here. But so far, I'm just looking at the equation itself. We'll discuss boundary conditions a little later. Okay, so mm, maybe I can actually. So I'm already out of time. But maybe actually maybe this is a good point to stop. I'm going a little slower than I thought, but is this a it's already 12:45, so maybe it's uh should I go on, or is this lunchtime? I don't know, or what. Okay, I'll go on for a few minutes more and then I'll stop. Okay, let me write. Okay, so the advantage is that of this equation is that we can immediately solve it, right? And so, what are the kinds of solutions that you get? Well, you get solutions which look like so. You want to solve the wave equation. In any case, the dt phi square term is just something that sits. You can always, when you separate variables, you can always solve for dt phi squared is equal to minus omega squared phi. Okay. So the kinds of solutions that you get are that phi is equal to e to the minus I omega t, okay, into e to the minus I omega r star, okay, or e to the I omega r star, okay. And we also need, even though the angular part didn't appear here, we also have to solve the angular part. There's the angular dependence of the field. And so I can also write down a YL omega, okay. But remember that this part, the dependence on R star, doesn't care about the value of L. It only cares about the dependence on T. So this is the solution near R equal to RH. And of course, apart from this solution, we have the Hermitian conjugates of the solutions. We have solutions which look like e to the plus I omega t and e to the plus I omega r star and e to the minus I omega r star here. Is this notation clear? What I've written here is that the solution looks like e to the minus I omega t into YL omega into either e to the minus I omega star or e to the plus I omega star. Okay. And the relevant part is whether the sign of minus I omega t is the same as minus I omega star, or whether this is minus I omega t plus I omega star into e to the minus I omega r star. This is solution 1, or the solution 2 is phi is equal to e to the minus I omega t e to the plus I omega r star into YL omega. Apart from these solutions, the Hermitian conjugates are obvious solutions. The reason I've written these solutions is because these are the solutions that when we quantize the field, will multiply the annihilation operators, the ones which have e to the minus I omega t, and of course we'll have the Hermitian conjugates as well. Okay, so there are two possible solutions, either this one or this one. What's the difference between this? The difference between these two is here you get t plus r star, here you get t minus r star. Okay, is this clear? Okay, good. Now let me say something about what these solutions are doing. Okay, so and then I'll stop. Okay, so let me say a little bit more about the horizon, and then I'll stop. Notice, we wrote down the coordinate system which looked like dr star is equal to, um, uh, dr star is dr by f of r. In that coordinate system, in this part we had r star going to infinity. Remember, we wrote that, right? And in this part we had r star going to log of r minus rh into twice kappa. So in fact, if you work it out carefully, you will see in this part we have r star goes to minus infinity. Okay. I also introduced some v and u coordinates which are unfortunately deleted. But if you look at what happens to the time coordinate as you approach this horizon, the time coordinate goes to plus infinity here. Okay. So here r star goes to minus infinity, here r star goes to plus infinity, and here t goes to plus infinity here. Okay. And so t increasing is this direction. Okay. Okay. So what is the physical interpretation of these solutions which have e to the minus I omega t into e to the minus I omega r star and e to the minus I omega t into e to the plus I omega r star. Okay. In these solutions, as t increases, okay, r star has to decrease to keep the phase constant. You see, because the solution looks like e to the minus I omega t plus r star. So as t increases, r star has to decrease to keep the phase constant. Therefore, these solutions correspond to ingoing solutions. Okay, so these solutions are solutions that enter the black hole. Maybe I'll draw the picture better. These solutions are called ingoing solutions. Okay, this corresponds to, let me call this phi in. Okay. These solutions, which look like e to the plus I omega r star, are solutions where the relative sign of e to the minus I omega t and e to the I omega r star is different. Okay. So these solutions have a factor that looks like t minus r star. So as t increases, r star also has to increase. So these solutions are called outgoing solutions. And if you see, if you ask what are the phases of constant t minus r star, remember t minus r star is also what appears in the definition of the u and v coordinates. Okay. So those are solutions which go this way. Let me use a different color. These are what are called outgoing solutions. Even though they're called outgoing at the horizon, they don't go out very much. They kind of go parallel to the horizon. Okay. So these are called outgoing modes and these are called ingoing modes. In fact, we have to be a little careful with boundary conditions as someone asked. And so, when we write down the solutions, we'll have to take a particular linear combination of these ingoing and outgoing solutions to get the right boundary conditions at plus infinity. But maybe I can do that after lunch. So I'll stop here. But what is the point I wanted to make? Okay, so as I said, I promised that every time, for those of you who get lost in the equations, I'll make some simple point. And the simple point is that near the horizon, the wave equation simplifies and we identify and these are modes which have the property that they go like e to the I omega t plus r star and e to the minus I omega t minus r star. Okay. Okay. So this was the third point that I wanted to make. Okay. Okay. So in this lecture, we basically only made 3 points. The first point was just about the classical black hole geometry. The black hole is in general a complicated object. It's formed by collapse. But if you go to late times, then there's an emergent late time isometry. The second point was, if you look at the horizon in the original coordinate systems, it looks like it's a singular region. But in fact, the horizon, if you go to the right coordinate system, just looks like a patch of empty space. And the third point we made was that near the horizon, the wave equation simplifies and you can identify clearly ingoing and outgoing modes, which near the horizon do this. One mode move like this, the other modes move like this. Okay. And the reason the wave equation simplifies is something that we saw. It has to do with the way we define these coordinates. We'll now come back in after lunch, and I'm going to use these to derive, or at least sketch the derivation of Hawking radiation. And maybe by the end of the next lecture, I'll introduce the information paradox. Okay, so that's all I wanted to say. Maybe we can have some questions and break for lunch. Yeah. Going out. What does that mean? You have to tell me what the state near the horizon means. What? Behind the horizon? At r equals, what does it mean? What does near mean? Is it slightly outside or slightly inside? No, if it's slightly, if it's no, what? No. If you define that the wave function had support only slightly inside, it'll stay slightly inside, right? Why will it? How can it come outside? What you're imagining is you have a state where there's, so you have to be a little careful about what those terms mean. But to the extent you can speak of a photon as a localized excitation, if it's inside the horizon, it can't come out. How can it come out? The horizon is a light ray. There's no probability for faster light transmission, right, in quantum field theory. Yeah. Gone. A precise way to say that is, if you act with a unitary operator that creates a photon behind the horizon, that does not affect anything outside the horizon. Yeah. Oh, thank you. Yeah. YL fire this. Thank you guys. Thank you for that question. YL omega are just the spherical harmonics. I just wrote them to give you a basis for functions in the sphere. What I said was, when I solved this equation, I focused on the T and the R star parts, but that doesn't mean that there is no dependence on the sphere. So these are just the spherical harmonics that solve this part of the wave equation. Remember, when I wrote down the Laplacian somewhere, yeah, there was also the Laplacian on the sphere. Okay, so Laplacian on the sphere is solved by these equations, which are called YL. They in fact also have a magnetic quantum number and other quantum numbers. I suppressed all of those because this is not going to play an important role in what we say. Okay, so this is just the part that solves the wave equation, but it's not important for me. Okay, are there other questions?